Hey everybody, this is day 2 of one problem a day, and this is one of the problems that I had asked on the exam for my university physics students. And it's a kind of interesting question. What you have is a stick 1.5 meters long and pivoted at its center, right about there, and a bullet is fired into it. The bullet is fired into it at 250 meters per second, and it makes a hole in it and comes straight out through it at a speed of 160 meters per second. The length of the rod or the stick is 1.5 meter. The mass of the bullet is really small, 1.5 gram, and the mass of the rod is 300 grams. So that is the situation, and you have to find the angular velocity of the rod, because what's going to happen is when the bullet passes out, assuming that there is no friction here at the pivot, this stick or rod is going to turn in the clockwise direction, and you have to find the angular speed at which it turns. Now, setting up a problem in physics is the most important part, and it is the most difficult part too, because you look at this and you think, can I apply the conservation of kinetic energy? Well, you can't, because when the bullet hits the stick, a lot of sound is going to be produced, some heat is going to be produced, and so kinetic energy is not conserved. A lot of kinetic energy is lost, so you can't work using kinetic energy. And also remember that the bullet hits exactly midway between the pivot and the end. So if the length of the stick is 1.5 meter, this is half, which is 0.75 meter, and it hits at the middle of that, which would be half of 0.75 meter, being 0.375 meter. So that's the situation. We can't apply the conservation of kinetic energy. So what do? Now, this is a simple case of application of conservation of angular momentum. Angular momentum. Now, what's angular momentum? There are several formulas for angular momentum. One of the formulas is taking the product of the linear momentum with the radius. Linear momentum is the product of mass and velocity. So you have the mass of the bullet, which is 1.5 gram, which you got to change into kilogram, and you have the velocity of the bullet. You multiply them, you get the initial momentum, and then do the same with this velocity, you get the final momentum. If you take the difference, you get the lost momentum. Now that should have been the momentum transferred to the stick. Okay? So if you multiply that with the radius, which in this case is this, you're going to get the angular momentum given to the stick by the bullet. Okay, so the angular momentum is the product of radius and linear momentum. And linear momentum is mass times velocity. Okay, so what I've done here is I've multiplied the radius in meters with the mass in kilograms, and I've taken the difference between the velocities, which gives the angular momentum imparted to the stick, which comes out to be 0.050625, and the unit is kilogram meter squared per second. So once you know that, now you have to know that angular momentum can also be calculated using I times omega, where I is the rotational inertia. In this case, the formula for rotational inertia is mass times the square of the length by 12. ml squared by 12 is the formula for rotational inertia of a stick. So when you do that, the 300 gram is 0.3 kilograms and the length is 1.5. Square that divided by 12 and you get the rotational inertia of the stick in kilogram meter squared. And then remember that the angular momentum is conserved, which means if you multiply this I with the omega, which I'm doing right now, 0.05625 times omega, you should get the angular momentum given to the stick, of course. So that's why I've set them both equal. And then omega is just this number divided by this, which comes out to be 0.9 radians per second. So that is the angular speed with which the stick will begin rotation. And I hope you understood this. This was a specific case of setting up the problem and using the correct principle, which in this case was the conservation of momentum. See you tomorrow. Thank you and good luck.